to pull up my notes. Voila. Okay, so I wanted to start off with something conceptual, and that is that here's K theory, here's motivic cohomology, and here's what Vesna talked about. And what I want to try to do is to sort of bring everything together. So that's my ambitious goal, and I may or may not succeed. So the first thing I want to mention is Chern classes. And if you take Kn of x, and I choose an I and an n, then let's see, so I guess 2i of x with coefficients twisted n times. I hope I got my indexing right. 2i minus no, it's I times. So the twist is the same thing as the I and 2i minus n. So if n is equal to 0, then we get k0 of x going to h2i of x with coefficients in zi. So these exist. And the construction of Chern classes is sort of a well-known piece of the literature, but it's sort of ugly and it involves lots of technical machinery. But there's a map from motivic cohomology to 2i minus n of x plus c, z if x is over c. And this map from here to here is the classical Chern class map that you get in topology. If I map to L-adic cohomology, then I get L-adic Chern classes. If I map to Deligne cohomology, 2i minus n x zi, I get Deligne Chern classes and so on. So pretty much all of the standard Chern classes that we know about that are operating on K theory factor through this universal Chern class. So that's the first connection between K theory and motivic cohomology. Now the next thing I want to do is I want to construct a category DM, which is good. And I'm going to have to do this in several stages. But here's the basic picture. I start off with smooth over K. So just for the sake of today, this is a field of characteristic 0. If it's not a field of characteristic 0, if it's a field of characteristic P, then you have to say lots of times up to something of up to P torsion. And I don't want to have to say up to P torsion a million times. So I'm just going to assume it's characteristic 0. But that's the only change that would happen if I did this in characteristic P for a perfect field. I just have to say up to P torsion a lot of times. So you have this, and you have Z transfers, and you have NST. So the fact is Navich, sheaves with transfers is what I'm calling NST, and it's an abelian category. It's actually a very nice abelian category. It's got enough injectives and whatnot. So now what we can do is we can embed that in the derived category of Nisneva sheaves with transfers. So what is that? That is the category of chain complexes of guys in this category up to quasi-isomorphism. Now inside of derived category we have DM effective, subcategory of all complexes F such that for all x in smooth over K, the cohomology of x with coefficients in F is the same thing as the cohomology of x cross the affine line coefficients in F. So in the literature, the way that this is described is that these are strictly A1 invariant, and what we want are the things that are A1 invariant, but there's a theorem that says that in this particular context, strictly A1 invariant is equivalent to A1 invariance. So we have this subcategory. Now, there's also a localization. So you take the derived category of the Nisneva sheaves with transfers. Inside of here you have DM effective, and there's a localization map going backwards. This localization map going backwards is the analog of the map that Vesna talked about with motivic homotopy theory. So I'm going to use this localization map to talk about DM effective. And now I want to do the following thing. DM is what I get from taking DM effective. And I remove so I'll write tensor Z inverse. So you universally invert the functor which sends M to M tensor transfer with Z of 1. So in order to do this, you notice that I snuck in a tensor transfer. So the thing that it characterizes is the fact that if I take Z transfers of X and I do this transfer map to Z transfers of Y, this is the same thing as Z transfers of X cross Y. So if you take any object in this category, any chain complex of which has this strictly A1 homotopy invariance property. If you take anything like that, you can resolve it by chain complexes which are just concentrated in degree 1, and so that once you know that what it is on those, then you can take any resolution and you just pop it in, and then you just use the fact that it's an abelian category, and you have no trouble making the definition. So what I want to do here is use my localization map to DM effective. Now let's see if I did this correctly. So I've defined DM effective right here. So that's the DM effective. And then I will think of this as as inverting minus 1. So I have this chain of functors which start with smooth schemes, this Navy sheaves with transfers, derived category of this Navy sheaves with transfers, effective derived motives, and DM. Now what I can also do is go to spaces, and I can go to spectra, and there's a functor which goes from here to here. That effectively is the functor that Vesna talked about. And there exists an adjunction and the effect of this is that we take Hn of x, coefficients in z parentheses I. This is the same thing as HOM in dm of z transfers of x into z parentheses I. But by adjunction, this is the same thing as homotopy classes of maps from x plus into, what did I write? I shouldn't have written I. It's a forgetful functor, so it should be U. For Umgebung, z transfers of I. And so this is in the category spectra. So when Vesna was talking about this, she talked about the fact that this functor is realizable. So U of z transfers of parentheses 0 represents Hz. And if I take U of z transfers of I, it represents Hn blank z parentheses I. So the point of all of this game is that we've basically spent the last couple of days building up the machinery, and now the machinery just sort of falls out of the woodwork that we have this category of derived motives. And here's an important property. If x and y are smooth projective, and homomorphisms in derived category from z transfers of x to z transfers of y is the same thing as homomorphisms from x to y in Grothendieck's child motives. And that's the category that was talked about in Scholl's talk. So this category DM, which we call derived motives, has the property that it contains the child motives, but it contains a lot more. And so that makes it a legitimate candidate for calling it something having to do with motives. The problem that we have with it is that this is a derived category, and here's a conjecture. Well, it's not a derived category of a thing, but it's a triangulated category, right? Let's be careful. So here's a conjecture, and there exists a T structure on DM so that the heart is the subcategory generated by the class of z transfers of x's. Well, x smooth projected, let's say. If this conjecture were true, then we would know lots of things. But that's the overview that we have. So okay. So the next thing I want to talk about is the slice spectral sequence. And I think that there was a minus sign difference between what I'm going to write down in so the spectral sequence looks like this: H00, H01, H11, H02, H12, H22, and so on, if this is a field. And if it's not a field, then we would have H1, H21, H32, H42, etc., like this up to the dimension of x in general. So there's everything is living in the, for a field, everything is living in the third quadrant. But if you don't have a field, you have a variety of a higher dimension, then you have stuff leaking over into the fourth quadrant. So for example, this is the Picard group of X. And so the filtration would be H00, H22. And this piece of the filtration is giving you basically the, this is the Chern class, this is the Chow filtration. Sorry? Well, she had, yeah, so the E2 P comma Q is H minus P minus Q of X with coefficients in Z minus Q. If P equals to 0, it's minus Q with minus Q. So I think this is right.
No, but this is the diagonal you wrote there, where P equals Q and all the first terms are 0.
So you think it's,
I think it's P minus Q.
Plus P minus Q. The trick is to look at this picture and figure out the indices.
Yeah.
And it's converging to K minus P minus Q of X, where X is smooth. Over K. Okay, now I want to give you one example of how this works. Now, what I want to do is I want to use two facts, and the first fact is going to be that H0 of K with coefficients in Z mod L twisted Q times is the étale cohomology of K with coefficients in mu L tensor Q times, and H n of K with coefficients in Z mod L twisted n times is isomorphic to K Milnor sub n of K mod L. So that means that what we have is Z mod L. Here we have roots of unity in Z mod L. Whoops. The Lth roots of unity in K. Here we have the Lth roots of unity in K times it twice, and so on. Here we have K star mod L. Here we have K2 of K mod L. Here we have K3 of K Milnor mod L, etc. And so the entire spectral sequence lives in these particular quadrant for a field. Now, let me stick in 1, H11, whoops, H12, H23, H13, mu L tensor 3 times. The point of this is that this is the first differential which is non-zero, and it goes from here to here. So in the beginning of this, you strip off K0 of K mod L is equal to Z mod L. And in the second one, you strip off the fact that K1 of K mod L is the units of K mod L. But that's because K1 of K is just the same thing as the units of K. Here what you get is an extension, 0, K2 of K mod L goes to K2 of K with coefficients in Z mod L, goes to the L torsion in the roots of unity, goes to 0. Now if K contains all of the Lth roots of unity, this is Z mod L. But for example, if L is equal to 8 and K is equal to the rational numbers, there's only 2 roots of unity, so this would be a Z mod 2. Okay, so let's suppose that K is an algebraically closed field. Then HP of K, if coefficients in anything is equal to 0 for P not equal to 0. So in this particular case, what we get is Z mod L, Z mod L, Z mod L, Z mod L, zeros everywhere else. So what you see here is that the K theory in degree 2i, 2, I guess it doesn't really matter, degree 2i of K with coefficients in Z mod L is isomorphic to Z mod L, and K2i minus 1 of K with coefficients in Z mod L is equal to 0. If you let L vary, so for example, you can take factorials, then this behavior tells you that the K theory of degree 2i minus 1 of K is isomorphic to Q mod Z, and I put in the I just for fun, direct sum something which is uniquely divisible. And K2i of K is equal to 0, direct sum something which is uniquely divisible, and that's for I greater than 0. So this is a calculation of the K theory of algebraically closed fields, which was first done in the 1980s by Suslin using very, very different methods. Of course, the spectral sequence didn't exist back then. Here's an open problem. And so the open question is, what kind of groups are these uniquely divisible groups? What can we say about them? Do they have any kind of structure whatsoever? We really don't know. The only example that we know is if I take the units of the field, that's isomorphic to Q mod Z plus a uniquely divisible group. So what is that uniquely divisible group? That uniquely divisible group is just the units of the field modulo the roots of unity. So for example, if k is equal to the complex numbers, there's some structure there. But if k is some other algebraically closed field, the structure is more complicated. But if k3 of k is Q mod Z plus uniquely divisible, and we have absolutely no idea really what that is. So this is one of the things that we don't know. Okay, now I have to start erasing. So Adams, Frank Adams, defined the E invariant on stable homotopy groups to be, so take pi 2i minus 1 stable, and they may be constructed as follows. So you take k pi I minus 1 and k 2i minus 1 of q. And you map this to k 2i minus 1 of q bar, which is isomorphic to Q mod Z. And so the image of this map from here to here is the E invariant that Frank Adams defined. So what we call the E invariant is just the edge map. Oops, I'm doing this for any field. Hang on for a second. Let's try writing this down again. So if you take any field of characteristic 0 and you take this composition of maps, you get a map from the K theory to mu L tensor I. So here's an example.
One question. In the definition of the invariant, what's the first map?
K2I minus 1.
I mean, in the first line.
In the first line, what is which map? This map?
First map.
This map is given by the fact that there's a functor from finite sets to K vector spaces. So what's the functor? You take a set, you take the free vector space on that set. And this defines a symmetric monoidal morphism. So from finite sets to K vector spaces. And so if I take the K theory of finite sets, I get a map from here to the K theory of vector spaces over K. Now, there's an N, there's an N. What is this map? This map is the first of the various constructions of K theory that I gave you in the first lecture. That I said if you have a symmetric monoidal category, you get one construction. If you have an exact category, you get another. This is the construction for symmetric monoidal morphisms. Well, the K theory of finite sets is just the stable homotopy groups. So the map goes from here to here. And that's the map that you asked me about. All right, so in K3 of Q, which is Z mod 48, we map it to K3 of Q bar, which is isomorphic to Q mod Z, plus some uniquely divisible group. Well, it's not an injection. The kernel is Z mod 2. So let's see, I can explain that. If I take that green arrow, the source of that green arrow is the K3 Milner of Q is isomorphic to Z mod 2. So if L is an even number, K3 of Milner mod L is just Z mod 2. And the map, which is the green map, it can be non-zero. So it's coming from HL of K minus 2. So it's the L-thwits of unity of Q. Tensor 2. And this can be non-trivial. So that green differential is non-zero in these particular applications. Okay, so let's see, where am I? Right. So here's an example where L is equal to 691. When L is equal to 691, then we know that H12 of Q, that's the is the first cohomology, étal, of Q with coefficients in Z mod L. Wait a second, I'm using this notation. Tensor 2, and that's Z mod 691. And so you get an element of order 691 in the K theory of the rational numbers. So this is sort of an idea of how you can use this spectral sequence, even if you don't have a good control over everything. Now let's see, where am I? That's the E invariant. What's the other map? The other edge map. So the map coming from K-theory to motivic cohomology is one of the edge maps. The other edge map is going from motivic cohomology back to K-theory. So it's K Milner, okay, with an N, mod L. That's the same thing as H N of K with coefficients in Z mod L, parentheses N. And that's mapping into Kn of K mod L. So what is this map? Vesna described this group a little bit. So she said it was generated by things in degree 1. So the AI are in K star. And you, that's the same thing as K1 Milner of K. So if you take a product of n of them, you get a thing in the nth K group. And we map it over here. This is just the product of A1, cup, A2, cup, AN, where the AIs are considered to be same thing as in K1 or in K1 Milner. So this map is a very standard map. And here's a theorem of Suslin. And the theorem of Suslin is this is an injection. Modulo n minus 1 factorial torsion. And so an example of this kind of thing is where K3 of Q, Milner, is Z mod 2. That injects into K3 of Q, which is Z mod 48. But K4 of Milner, which is also Z mod 2, to K4 of Q is equal to 0. So sometimes the map is an injection, but it's not always an injection. And by the way, there's a conjecture. Oh, no, this is a theorem of Soulé and Rognus that K4 of the rational numbers is equal to 0. So this map had to be 0 anyway. Okay. Mark, when does my lecture end? I was thinking I was going to end it at 3:30. We'll see what happens. So let's choose a totally ordered number field. Not totally ordered, but totally imaginary number field. Okay. So for example, I could take the Gaussian rationals. Anyway, I want to let R be the degree of K over Q divided by 2. So if I didn't have a totally imaginary number field, then the degree of the thing would be R1 plus 2 times R2 is equal to the degree of the extension. And I'm simplifying things. So the étale cohomological dimension of K is 2. So that means when I write down my spectral sequence, so this is the L-threads of unity. Well, this is K star modulo L. This is K2 Milner mod L. This is H12. And then there's a 0. And so here I have an H0. I have an H. This is a 0, 3, H1, 3, H2, 3, and a 0. And so here is a 0 as well. So if I'm looking along these diagonals, what I see in every single diagonal is a bunch of zeros, and one term in odd degrees and two terms in even degrees. There's absolutely no place for differentials to go. So the conclusion that we get out of this is that, let's see, so this is 2, 4. So K2I of K with coefficients in Z mod L is isomorphic to mu L tensor I of K. That's the E invariant. And then there's another term which is H2 étal of K, and its coefficients are units tensor I minus 1, I plus 1, and H in K2I minus 1 of K with coefficients in Z mod L for odd ones is equal to H1 étal of K, and the coefficients are, did I do this right? Yeah, tensor I. So we get a calculation of the K-theory of totally imaginary fields. You can jimmy this up to a calculation of the K-theory of arbitrary number fields if you're allowing yourself to play around with Z mod 2 torsion. And the point is that the same trick works for all number fields when L is odd. So we can't say much about the even torsion without doing a lot of calculations, but we can do the calculations, and they are written down in various places, for example, in my K book. Okay. Maybe I do one more example and then I stop. Suppose X is a smooth elliptic curve. Well, in fact, smooth curve over the complex numbers of genus G. So then what we know is that the étal cohomology of X with coefficients in mu L tensor I is the same thing as the nth cohomology Betty of the corresponding Riemann surface. With coefficients Z mod L. So this is the comparison theorem, and I'm using the fact that the complex numbers is algebraically closed, and I'm using the characteristic 0. So then what we do is we also have cohomological dimension. Two. So we get something which looks very similar to this. So here's Z mod L. Here's 0. Here's the Picard group of X mod L. Here's 0. Here is this is O of X star mod L, which is 0. Here is Z mod L. Here is Z mod L. Here is H1 of X. So I'm just going to write Hn of X for this group, so that I don't have to write all of the rest of the symbols. Here's H2 of X. Here's Z mod L. Here's H1 of X. Here's H2 of X. Here's 0. Here's Z mod L. Here's H1 of X. Here's H2 of X. Here's 0, here's 0, etc. So what you have, again, is a sliding periodic thing, and there's no differentials. H2 of X with coefficients in Z mod L is the L torsion in the Jacobian. Which I think earlier was called pic of X. Pic not of X. And so we get the same thing in every single even degree. So we get the K theory in degree 2i of X with coefficients in Z mod L. It's isomorphic. Now I want to get my twist right. I think I've done this wrong. If H1 of X, coefficients in Z mod L, that should be the L torsion in the Picard group. And H2 of X, coefficients in Z mod L, should be Z mod L, because it's H2 of X, Z, tensor Z mod L, by Poincare duality. So what I just wrote here is wrong. This is the L torsion in the Picard group. This is the L torsion in the Picard group. Whoops, 1, 2, 3. Here, this is the L torsion in the Picard group. So what I get here is Z mod L plus Z mod L. If I is even, well, and this is the even case, and K 2i minus 1 of X with coefficients in Z mod L is isomorphic to the L torsion in the Picard group of X, which is the same thing as a Z mod L to the 2g, where g is equal to the genus of the curve. So the point of this is that we can do calculations that we couldn't do before, that if you want to understand what the K-theory of these things are, all you have to do is just compare K-theory to motivic cohomology, and then just compare motivic cohomology to Weibel cohomology, and then just look in your standard textbooks. So that's what I've done, and I'm going to stop early. Thank you very much. Some of them are non-zero, and some of them are, a lot of them are zero. The only one that's easy to show as non-zero is when you know that the Milnor K-theory doesn't survive. So for example, if you're, well, I can't get it down from here, but basically what you know is that K4, Kn, Milnor of Q is equal to Z mod 2 for all n greater than or equal to 3. And these die in the K-theory of Q for n greater than or equal to 4. So they get hit.
Do you read that off without knowing it ahead of time? And do you read that off in the spectral sequence, or does that tell you what the differential is in the spectrum? Which way does it say?
Okay, so the calculation of the Milnor K-theory
Yeah, that's okay.
is like 1970. Jack Milnor did that. The fact that they die in here is something that you can see in a more elementary way, because -1 is the non-zero symbol, and this dies in K4 of Q because why? Because that's 0. So that would just show you that everything has got to get hit. Everything on the y-axis has got to be hit below the green line.